Did you share
I
already؟
am دكتور. Yes, I shared.
مش شايف حاجة، أنا مش عارف ليه.
Do you guys see this the screen or because I can see it from my side, but I joined
I
earlier.
can see it too.
No, I don't see it.
Me too.
Okay.
Okay, so maybe if
Can you sign off on the sharing and okay,
There
now
we
it's
go.
okay. Now it's clear.
Okay.
Now.
Okay, thank you for your
That's
feedback, Dr. Mohsen and Dr. Ala. So Dr. Amr received his master and PhD in electrical and computer engineering from University of British Columbia 2001 and 2006 respectively. He worked as an advisory IT specialist in IBM in Vancouver for almost 10 years, taking leadership role in system development for vertical industries. He's currently professor in the College of Engineering, Qatar University. He has 25 years of experience, wireless networking and industrial system development. He holds 3 awards from IBM Canada for his achievement and 4 Best Paper awards from IEEE conferences. His research interest spans wireless networking, edge computing, IoT. Dr. Amr authored and co-authored over 200 referred journal and conference papers, text books and books chapter in reputable international journals and conferences. He served as an editor for 2 international journals and has served as TPC and co-chair for many IEEE workshops. Thank you, Dr. Amr, for accepting our invitation. Please go ahead.
Thank you, Dr. Ayman. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, everyone. This work has been done in collaboration with many stakeholders in Qatar and organizations, academic organizations like UNRF, American University in Beirut, HMC, Temple University, University of British Columbia, and Manhattan College. So the outline of this talk is, first, I'm going to go through some motivation for pervasive AI and what it means. Then I'm going to talk about 2 major branches, applications for distributed inference, and I'm going to explain what that is, particularly for security and for multi-drone systems. Then I'm going to talk about applications for distributed learning, including federated learning, for IoT applications and multi-agent reinforcement learning for smart health. And then I'm going to conclude the talk. So as a motivation, as we all know, IoT was first coined in 1999 by Kevin Ashton from MIT, and it's evolving to dominate the market with more than $1.5 trillion by 2025. IoT together with AI constitute the 2 most critical technologies that will shape the future of the internet, with all the top companies which are currently overtaking even the ranks from the energy companies and so on, like Apple and Google and all these companies. They are all adopting AI technologies. Recently, in 2012, we started to have the paradigm of edge and fog computing, which is also growing exponentially to address some of the scalability issues in IoT architectures, as we will see in a minute. So all these 3 technologies, they are integral and critical components for the Industry 4.0 revolution that we see today. So traditional IoT, and cloud architectures, they rely on IoT devices as like mere data collectors that collect blindly the information that constitute some characteristics from the environment, and they send it directly to the cloud in a massive data streams over 5G networks. Of course, this type of architecture creates or causes some scalability issues because of the fact that all these massive data streams, they actually put loads not only on the cloud but also on the 5G network. Of course, in that case, the intelligence resides only in the cloud where the AI models they reside, and they perform all the intelligence at the cloud level. Other issues like in the storage, where the raw data gets sent from these IoT devices and they get stored into the cloud with massive amounts, and some of this data is not even relevant, and some of it is actually not cleaned, and it's actually in some cases garbage. So this also puts some load on the network. So from the network perspective, the bandwidth provisioning for the IoT devices is a very challenging issue. Also, from the IoT point of view, we have issues like energy consumption, where the devices are very energy hungry to try to send this raw data in massive amounts to the cloud. We also have some security issues because some of this data is not even cleaned, and in that case, you have some data integrity issues that some of the raw data that reaches the cloud are not really relevant to the AI intelligence on the cloud. And also some of this data is actually sent as pure information. So you have some privacy issues as well, that someone could tap into this data and read some private information. So all of these issues has mandated or motivated the evolution of edge computing, as you all know, where we actually push the part of the intelligence from the cloud to the edge, to a designated edge nodes, where these edge nodes, they collect and summarize the information from the IoT devices and send that over the network in a more clean and more intelligent way. In which case, this edge computing paradigm solves many of the issues that we talked about in terms of scalability, the storage, and they can interact with the 5G network more efficiently, in which case they use the bandwidth more efficiently. Because of the fact that you can use some energy efficient radio technology between the edge and the IoT nodes, because of the proximity of these edge nodes to the IoT devices, you have less energy consumption, and you also all the security and privacy issues can be resolved at the private network level between the edge and the IoT devices. Of course, this creates more challenges in terms of deployment complexity, because these edge nodes, they have to be deployed in strategic places, and also you have extra infrastructure by deploying these edges, and sometimes they actually merge some of these edges with the IoT devices, in which case you have some issues with the limited resources of the IoT devices. So this paradigm is currently evolving to what we call pervasive edge architecture, or in other words, democratized edge computing, where the intelligence is actually pushed one level down to the IoT devices themselves, where we actually distribute both on all the IoT and the network resources in the 5G network. And we do that strategically to try to address all the resource constraints that these IoT devices have. So some of the issues like deployment complexity is reduced. We don't have to have designated edge nodes and so on. However, we still need to address some limited resources. In fact, it's more challenging in the case of pervasive edge computing, where these IoT devices are more resource constrained, in which case we have to distribute both the communication resources and the computation resources more strategically in that case. So this pervasive edge computing creates a new paradigm of communication versus computation, where we need to actually have both the access points and the IoT devices strategically positioned, and we have to distribute the computation amongst all these network and IoT devices strategically, in which case we have pervasive edge computing. So pervasive edge computing is about smartly distributing the computation and the communication. So when communications meet computation, the idea here is that if you compute efficiently and compute more, then you can communicate less, and vice versa. So how to address the trade-off between where to compute in order to communicate less, in which case you can utilize the network resources and the computation resources efficiently. So when we combine the pervasive edge computing with AI, and in that case, what we try to do is to make the AI models more pervasive and more efficiently distributed amongst the IoT devices and the base stations in the network if needed. Then we have the paradigm of pervasive AI systems. So as some examples of the operations that can be done on the pervasive edge nodes using AI, we can perform data cleaning and preprocessing. We can perform adaptive compression, where we can efficiently compress the data before transmission. Hence, we can enhance the efficiency of delivering this information over the 5G network. We can perform some feature extraction. So instead of sending the raw data, we send features. We can detect the state of the user, and we can predict the state of the user, and based on that, we can do some inference or classification. We can ensure security and privacy by performing some security techniques of the data before we send it. And we can even perform some access network selection, as we will see. So some of these functions, these highlighted operations, are the ones that we will focus on throughout the remaining part of the presentation. Some of them will be done using AI, as we will see. So with that motivation, we try to divide, or we try to have this taxonomy about the pervasive AI systems, where we divide the pervasive AI systems into distributed inference. And by distributed inference here, I mean that we have a pre-trained machine learning model that we need to distribute amongst the IoT devices in such a way that addresses the resource constraints on these IoT devices and minimize the time required for performing this inference, as we will see. So in this branch, we will talk about distributing the machine learning model signal-based or layer-based, and we will see the difference in the pros and cons for each one. This branch, this area, for those of you who are trying to get into some distributed AI and machine learning areas, this area is not widely explored. And I will talk about two use cases in this branch for IoT security and mobility for drones. The other branch of distributed learning, in that case, the machine learning model is not pre-trained. It has to perform the learning in a distributed way. And this particular branch is very, very widely explored in the literature. You have the well-established area of federated learning, where you exchange the machine learning model weights between the IoT nodes. And you have the other well-established area as well, where we use multi-agent reinforcement learning to perform some distributed optimization using some distributed agents, as we will see. So I will talk about a specific use case for each of these sub-branches as we move forward. So first, I'm going to cover the distributed inference, where again we have some pre-trained model that we need to distribute amongst all the IoT devices. And in that case, we have an intensive machine learning model like VGG16 or VGG19, or some of these intensive machine learning model. And the idea here is to try to divide this machine learning model strategically amongst all the IoT devices in order to address a certain performance metric. So objectives here are to optimally distribute the machine learning model amongst the IoT devices and to address the resource constraint of these IoT devices in order to minimize the latency and parallelize the computation amongst multiple requests, as we will see in a minute. And the challenges here are, of course, the resource limitations on these IoT devices in terms of computation, memory, and energy, and so on. And also how to distribute this machine learning model in such a way that preserves the security and privacy and prevent any kind of black box attack and any kind of reverse engineering to the actual data, as we will see. And on the other side, we address the network dynamics, such as mobility for the case of mobile IoT devices like drones, as we will see. So to talk about the first use case where we need to strategically distribute the machine learning model on the IoT devices to address some security for IoT network, we have this smart city IoT system where you capture an image from an original source surveillance camera, and you need to identify the person in that image through intensive machine learning operation using, like, for example, VGG19 or some of these well-established machine learning architectures. So the idea here is that how to divide the machine learning model into segments and strategically position these segments to the different IoT devices in such a way that will minimize the latency or the end-to-end time required to identify the person in the image, and at the same time prevent or avoid any kind of reverse engineering from an illegitimate node that tries to reverse engineer that image. So by segments here, by the way, we mean that we divide the actual layer into smaller segments, and each segment here includes a set of feature maps, or in other words, some kernel filter using the terminology of convolutional neural network, such that each segment can perform the operation separately, and we'll see how to do that. So the idea here is that from the source node which captures the image, we need to divide the machine learning model into feature maps, and we divide each layer into smaller segments in such a way that we have a set of requests coming from different sources, and we need to, for each request, we need to perform the end-to-end inference operation by dividing the machine learning model into segments at each IoT device. So, for example, we divide the CNN model into the VGG16 or VGG19 into like the ReLU layer, the conv layer, and so on. And we need to divide each layer further into segments, and then position strategically these segments at the different IoT devices. So this strategic distribution or efficient distribution of the feature maps into the IoT devices needs to address the parallel computation for concurrent requests. So we have multiple requests coming from multiple source nodes. We need to do it in such a way that avoids that any tampering that happens at each or any of these levels, that if you try to reverse engineer the actual data from any stage, that this needs to be avoided. and we also need to abide by the resource limitation of these IoT devices. Okay. So to do that, the first thing we have done is that we have conducted some black box attack analysis, where we try to use a model to try to reverse engineer the actual image at different levels of the CNN model. Okay, and the main conclusions that we have reached here is that if you notice, as you go deeper, and this actually makes perfect sense, as you go deeper in the layers, you will not be able to extract clear data, or the reverse engineering would be harder. Also, when you divide each layer into segments, okay, so the less number of feature maps you have access to, again, the harder the reverse engineering would be. And we have conducted this on two very well established data sets, and then we have constructed this lookup table using a metric called the structural similarity index measure, where we try to reverse engineer the actual input image from different levels and from different feature maps, and then we try to estimate the similarity index. So using this table, we can then try to say if we need to have a similarity of like, for example, up to 0.3, so we need to keep the similarity at maximum 0.3. So in that case, we need to have access to only 32 feature maps per layer, and that will allow us to kind of identify the split point where we need to divide the different layers into segments. Okay. So by doing this, we try to construct this optimization problem where we try to minimize the latency of performing the inference operation end to end, from the source all the way to constructing the or performing the classification. And we try to minimize this latency, which is a function of some network parameters, like, for example, the length of the segment, the actual data rate that this node has, the computation latency, and so on. And of course, this maximum is because we need to, each segment would have access to multiple devices. So we need to synchronize the data here. So we need to calculate the maximum latency across the different devices that belong to one specific layer. So with that, we need to minimize this latency end to end, subject to some constraints. The first constraint would be on the actual memory size of the IoT device. So all the segments that are assigned to this IoT device are able to be stored inside this IoT device. We have also some computational limitations on the IoT device. So this constraint tries to guarantee that the computations required by each IoT device can be, in fact, performed given the capabilities of this IoT device. And we also need to address the network bandwidth constraints that this device can have based on the radio technology that this device has access to, whether it's like Wi-Fi or 5G and so on. And last but not least, we need to also meet the security requirements through the black box attack using the similarity index measure that we have conducted in the previous slide. So, of course, this optimization problem is non-linear in nature, and also it has combinatorial complexity. So the proposed technique here is to try to devise a heuristic technique which can work in real time based on receiving a single request. So of course the algorithm is too long, but in brief, the way that this algorithm works is that first, after initialization, I receive each request and I perform this logic for each request, and this logic basically is divided into 2 or 3 different parts. The first part is basically for each request we assign the first and last layer, fully connected layer, to the source device, and then perform the split point based on meeting the security or the similarity index measure, and then we try to assign the different segments that are split using the SSIM to some IoT device helpers based on minimizing or based on addressing the trade-off between the latency and minimizing the bandwidth requirement, or the rate requirements on this IoT device. And we try to do that across the different split points. And if we can't, then we have to reject the request based on the fact that the resources on all the IoT devices are exhausted and we cannot accommodate any more requests. So the heuristic algorithm has been tested across different number of IoT devices, and as we can see, as the number of IoT devices is low, we tend to reject more requests. So we have to reject multiple requests, more than 70 or 80% of the incoming requests, because of the fact that the number of IoT devices available are small. So we don't have enough degrees of freedom to accommodate the different requests. And of course, as the privacy level gets more stringent, for privacy level 0.4, we have to, of course, divide each layer into more and more segments, which requires more devices to be engaged in the inference operation, in which case the constraints become more stringent, and we have to of course, reject more requests, as we can see on this green curve. So this is despite the fact that, for privacy level 0.4 or for more stringent constraints, we see that the amount of shared data between the IoT devices is in fact higher compared to the other IoT devices. However, this shared data is allowed to be more parallelized, and in that case, more and more devices, they get engaged into the inference operation, making the parallel computation of multiple concurrent requests possible in that case. So that's why the latency that's why we see that the latency, surprisingly or interestingly speaking, the latency for the privacy level 0.4 is actually less in that case, because of the fact that we, by dividing the layers into smaller segments, we need to engage more and more IoT devices, in which case they use different lengths, and in that case, the latency would be less. Also, we have tested this under different IoT network configurations, where we have in some configuration we have 70% small IoT devices. By small IoT devices, we mean like a Raspberry Pi, small Raspberry Pi, with of course less resources, and 30% of the IoT devices would be like a Nexus mobile device, which has more capabilities in terms of computation and memory. And in that case, of course, when the small IoT devices are the majority of the IoT, the latency tends to be more. And not only that, we tend to have more rejections. So there is about 29% rejection of requests for the case of the majority of small IoT devices. Okay, so another approach which is completely different to solve the same optimization problem is using reinforcement learning. And I assume that you all have some idea about reinforcement learning as a tool, as an efficient tool to solve optimization problems. And in that case, we resort to using a single agent reinforcement learning that tries to learn the evolution of state transition in the system, and tries to learn that transition of states, and then convert that to a set of actions which constitute a policy over time that tries to maximize a certain reward through some suboptimal solutions or suboptimal actions. So of course, the reinforcement learning algorithm in that case will try to learn the best set of distribution of these segments for the machine learning model across the IoT devices in such a way that meets the resource constraints and minimize the latency of the inference operation. So so instead of trying to devise a two-dimensional matrix of actions that would try to learn the location of each segment in the IoT devices, we have done this in a chained operation like this. So we, based on one state of the system, we try to allocate segment by segment. So the action of the agent at a certain point of time would be just a vector that would represent where this segment should be located in which IoT device at any point of time. And we do that iteratively until we allocate all the segments in the machine learning model strategically across all the IoT devices. So in which case, the actions for this agent is going to be, the actions of this agent is going to be like a vector of binary variables, which represent where a segment is allocated on which IoT device in the network. And based on this action, we get to a network state which takes a specific CNN machine learning model, whether it's one of the models that we talked about, whether it's a VGG16 model or a VGG19 model or any other CNN model. And it puts and what is the current layer, what is the feature map, what are the memory constraints on all the IoT devices, what are the data rates, what are the computational capabilities, and so on each IoT device. And based on that, we calculate a reward based on meeting the conditions or the constraints of the optimization problem, and try to estimate the reward, which is based on this formula here. And for this case, this part tries to engage the minimum number of IoT contributors to the inference operation, and this penalty here constitutes the cost that I have to pay in order to position a specific segment in one of the IoT device, based on calculating the data shared and the computation required by this IoT device. So we try to perform certain random actions, and then based on these random actions, we calculate the states of the system and the reward that corresponds to this. And we keep doing that across the different episodes until we find, or until we reach to an optimal policy that will try to minimize the latency subject to the resource constraint on the IoT devices. So of course, typically, The first thing we do for reinforcement learning is to analyze the convergence of the algorithm. And this result here shows the convergence of the algorithm and for reinforcement learning. Interestingly speaking, for the latency results here, if you notice, when we use one homogeneous machine learning model for all the requests, the incoming requests, we see that in comparison to the heuristic technique that we talked about before, the reinforcement learning unexpectedly does not outperform the heuristic. So that shows that on one hand, the heuristic algorithm that we have devised before is really efficient and is really robust in giving like good performance for the latency. But more importantly, because of the fact that the requests are homogeneous, so there is no like stochastic nature of these requests where the machine learning model of the reinforcement learning agent does not have to learn a specific pattern of these requests. So that's why the reinforcement learning in terms of latency does not outperform the heuristic technique as we would have expected. That's why we tried to study the heterogeneous case where the incoming requests could actually have different CNN models based on some probabilistic aspect. So that's when we start to have some performance enhancement for reinforcement learning, and we started to see some less request rejection as opposed to the heuristic technique. So for reinforcement learning, we started to see 28% request rejection as opposed to 40% for the case of the heuristic technique. So that gives us at least some insightful conclusion that reinforcement learning is not really the magic word for all optimization problems. So if your problem has some stochastic nature and there is some stochastic process that it needs to be learned by the deep reinforcement learning, that's when reinforcement learning really becomes an efficient tool for optimization. All right, so moving on to the second use case where
Dr. Amr, I don't know if people have questions at this point.
Yeah, feel
but
free.
I was wondering, just to give maybe 30 seconds, if people want to reflect. And
yes. Yeah, I think you have a very good point here. Yes, so I need to pause here and wait for some questions if you have any, and I would be glad to answer any question you might have.
yes,
So
yeah.
Go ahead. Do you have a question?
So does anybody have a question? So I have a small question, just related to. So do you believe the reinforcement learning in this case will give you better outcome with more complex, like you are seeing here with maybe VGG, or maybe with more complex type of machine learning model? Do you think it will get better results?
Oh, the real value of reinforcement learning comes when you have a probabilistic state transition of the system. Okay, so the system is not deterministic, because if the system is deterministic, really reinforcement learning does not it's not that efficient, or it doesn't really provide the performance that you would expect. So that I actually explained that here in the results. So when you have incoming requests that use the same type of machine learning model, so in that case, regardless of the arrival process of these requests are homogeneous, in which case the requirement for each request is actually deterministic. So you know exactly beforehand what machine learning model you want to distribute at which point of time, okay? Because they are all the same. right? So that's why actually the reinforcement learning, as you can see here, in terms of latency, the latency here is similar to the heuristic, and in some cases it's actually in some cases it's less, slightly less, and in some cases it's more. Okay, so so in this case, for example, the heuristic outperforms the reinforcement learning. The heuristic based on greedy algorithm that we have explained really slightly outperforms the reinforcement learning because the requests are homogeneous in the sense that they are all based on one machine learning model, which is like, for example, LeNet or Cypher or something like that, right? If the incoming requests, they probabilistically use different machine learning models, then you have to kind of predict. You have to have a sense of prediction, okay? That like after some time, after like 2-3 minutes or something, most probably I'm gonna have a VGG19, which is very, very intensive in terms of computation. So I better try to clear my memory of the IoT devices from now, so I prepare myself beforehand for the upcoming intensive request. That's what reinforcement learning is good at, right?
Yes.
But if there is no such prediction required and everything is deterministic, the greedy algorithm is good enough. In fact, it may actually, in fact, in some cases, outperform reinforcement learning, because reinforcement learning is based on suboptimal actions at specific point of time. But these suboptimal actions are believed to lead to very good performance on the long term, not on the short term.
Yes.
Right? So that's where reinforcement learning is really powerful. If you don't have this configuration in your system and the states of your system is kind of deterministic, reinforcement learning is not going to give you any better performance as you would expect. Okay.
Yes, thank you.
So yeah, this is based on the fact that reinforcement learning are fundamentally based on the market decision process, and it's the fundamentals or the key engine of reinforcement learning is based on market decision process. So it's based on the fact that the state transition of the system is stochastic, and there is certain transition probabilities from one state to another. So what reinforcement learning tries to do is to devise the policy that would lead to the best transition from one state to another that over time would lead to a good performance.
Yes. Thank you.
Actually covering reinforcement learning requires a full course on its own. But here we're just trying to move fast.
Yes.
So the second use case.
I'm sorry, and I have a question. Sorry, Dr. Amr, how are you doing? Assalamu alaikum.
Alhamdulillah.
Yeah, so, and I just want to elaborate more on this reinforcement. So in this case, so the probabilistic here is terms of the request that's coming. So you are actually, this is your probabilistic. So you have in your request some like Markov model process that your reinforcement learning are trying to detect. That's what it is saying. That's right?
Exactly. So the probabilistic nature in this context here is based on the fact that you don't know what is the machine learning model you will distribute next. It could be like VGG16, it could be LeNet, it could be Cypher, It could be anything. And yeah, so that's the probabilistic nature that really reinforcement learning starts to have some performance enhancement in that case. But if all of the requests are the same, they are homogeneous, okay, then there is no benefit of using reinforcement learning. And the heuristic technique can perform the same, if not even better.
Okay. So sorry, maybe my question is kind of so if I understand that you are trying to select which IoT device you are going to pick to optimize your resources, that's right, to optimize your performance at them. So does the reinforcement learning author trying to learn this, how he is going to optimize or find the optimal IoT, or is always trying to detect what's coming and then? So I need to know how the reinforcement learning with the two systems are working.
I need to go back. So the objective here, Dr. Muhammad, is to try to perform an action, and this action in that case is what segment of the machine learning model would run on a specific IoT device. And by machine learning model here, so we have this is the machine learning model. Okay, it's a complicated model. Okay, so we divide that CNN model into small segments. Okay.
Okay. Yes.
Yes. So these segments should be strategically distributed on the IoT devices in such a way that minimizes the latency of the inference operation end to end.
Yes.
Okay. So based on the incoming request, this DRL agent will try to learn that now these segments should be positioned on these IoT devices in that way, so that in the future, when I get more intensive requests, I need to position them on different IoT devices so that I enhance the performance in terms of end-to-end latency. Is that clear? So the stochastic nature here for this particular context is based on the fact that the incoming requests are heterogeneous in the sense that they use different CNN models. So
you are trying
the reinforcement learning implicitly predicts what requests are coming next, and based on that, they strategically position or take an action to strategically position the segments at this point of time. Not to optimize the instantaneous performance, but try to optimize the, you see what I mean?
So you optimize the log, so like if you look at the whole, it's a log term, over averaging, is this. So you can estimate what's coming next. So when you look at the whole, when you try to optimize the total latency, so you know what's coming next. So you can, your decision now, because you need to, you are predicting what's coming next. So your resources are optimized, taking consideration what's coming next. Okay. I have, I'm sure if I have one last question, So I didn't understand the part of privacy here. How does privacy is captured in this?
This is a very good question. Let me try to explain that part again. So by privacy here, we mean that if for example, I put one segment in one IoT device, okay, anyone who tamper the output of this segment can easily try to reverse engineer and get to the original image. So so this is the original image. Okay, so we conducted analysis using black box attack, okay, where we try to reverse engineer the image at different layers. Okay, so so logically, if we the deeper, okay, the deeper in the model we go, okay, the more difficult the reverse engineering would be, and that's a fact, and this is proven through this analysis. So deeper we go in the model, okay, the harder the reverse engineering will be. So this suggests that you need to position more layers in one device. Okay, but of course, this will not give you enough degrees of freedom because you do not have the memory and the computational requirements on one IoT device, right? So we also conducted the same black box attack if you try to divide each layer into smaller segments. By segment here, Dr. Muhammad, I mean that you have access to limited number of feature maps. اللي هي basically kernel filters in the CNN layer. So if you have access to 4 filters only, you cannot really reverse engineer and get to the original image by any means. What you get is nothing related to the image. So this suggests that for security, it's better to divide the layers into segments and distribute the feature maps across more and more IoT devices. This way, you can address the privacy issue. Okay, So that's why for this particular context, we say we categorized it under the segment-based distribution.
Okay, but this is related only to images, or this can apply to any type of machine learning model, or and this is
remember, yeah, it depends. It depends. You're right. It depends on the application. So for this particular application, we are using a surveillance application using this Salipa data set or CARS data set. And for that, we use CIFAR and, we use the specific machine learning models like VGG16, VGG19, LeNet. These are some well-established machine learning models. You're right. If you, for other applications, actually distributing the segments is not needed. You can run the whole machine learning model on one device and that's it. So you don't really need to distribute the nodes, in which case you can run all the machine learning model on one device and that's it. And this is in fact the case pretty much for simple machine learning models like LeNet. LeNet has only 2 layers, 2 CNN layers. So you find that you can really run this simply on one device. However, for security, you may want to divide these 2 layers into segments in some cases. Okay. So in the results in the paper, by the way, I can send the paper to you because it's not published yet. Or at least one of the based on the optimization is accepted in Globecom. We provide rigorous results and analysis based on the different types of machine learning models and how they can be distributed across the different IoT devices and how many devices you need to parallelize the requests and the computation for the inference operation.
That's excellent. Yeah, good. I understand it better. Yeah, I'm done, but unfortunately I need to leave because I have another lecture I need to give now. But Dr. Ayman, please, I need the recording. It's very nice. Yeah,
yes, inshallah. I will keep the recording. Thank you, Dr. Mohammed. I like questions as usual.
So yes.
It's a very nice work, mashallah. Very nice work.
I tend to go fast, by the way, but I thank you very much for the questions because the questions really help me to illustrate.
No, you're not going fast actually, but mashallah, the amount of information you're reading very well and deep. It's like we cannot, and for me, I cannot digest all of these nice things. Yeah, but it's very nice. Yeah, you're talking very well, and mashallah. It's almost enjoyable lectures. Okay. Okay, inshallah. Okay, assalamu alaikum. Thank you very much.
Salam wa rahmatullahi.
Dr. Amr, I have a question if you don't mind.
Please.
Yes. So yeah, thank you for sharing the work. I don't know if you recall Amr back in the days, I remember meeting you. I believe it was in Spain when you were talking about this stuff just verbally. You had this vision talking about it. So right now I see it in action, actually. It's really very nice to see it coming along and all of this progress made. So my question is the following, I would like to carry your idea to the extreme. What if, what happens if we just, take a single neuron and just, let every single IoT node coincide with a neuron? I know that communication will be much more. I know that latency will be much more. But do you think this kind of structure in which really the neural network is totally distributed, do you think that there is a class of applications that might benefit from this? And another thought that I want to ask you about is the following, how do you handle the reinforcement learning? How would it handle churns? IoT nodes come and go, right? So the environment essentially is dynamic. So the policy that you learn needs to, adapt to the environment as well over time. So is that something that will delay the policy itself or the development of the policy over time?
This is a very good point. Let me start from the last part, Dr. Ala.
Yes.
You are perfectly right. The network dynamics that we have addressed here are only based on the heterogeneity of the incoming requests. But you are perfectly right. if nodes come and go, that creates another dimension of network dynamics that is not addressed in this work.
Okay.
However, it could be really taken into consideration by, again, removing or adding IoT nodes into the network probabilistically over time. Okay, and again, perform the same reinforcement learning, okay, on what is the pattern of removing and adding these devices in the network. And based on that, we can, I believe, that reinforcement learning would really be a very powerful tool in that case, that would enhance the performance even more. So the more dynamics and stochastic aspects that you introduce into the system, the more powerful the reinforcement learning will be. That's what it can do best. But again, because of the fact that the requests were totally homogeneous at the beginning, so we did not see any performance enhancement. But you are perfectly correct. If we introduce network dynamics by adding and removing nodes, we should start to see more performance enhancement for reinforcement learning compared to the heuristic. As for the extreme case, that's an interesting point. I really don't know, and I do not see a specific application for a single neuron IoT device. I don't see why we need to do this, but it could arise in the future. I really don't know. But what we can learn from this work, by the way, is that the smaller the segments are, the more interesting scenario you're going to have, because you need to distribute more and you need to engage more and more devices, which in fact leads to less latency end to end. Okay?
Okay.
But here what we did is that the segment is proportional to the computational and memory resources on the IoT device. Okay? So if for example, the memory and the computational capabilities on the IoT device can handle only one neuron, then we can do that. We can do that. It's part of the work. But of course, the assumption is that we have significant resources, at least even the Raspberry Pi, it has like 2 GB memory. So it can handle really a significant number of segments and process different segments for different requests. But for single neuron, I don't know really, to be honest. I don't know if there is a specific application for that.
So, Dr. Amr, like, don't you think that synchronization will be an issue here? Like, I'm concerned about synchronization is not an easy problem in here.
Yes, I like these questions very much. You are perfectly right, Dr. Sah. You are hammering the nail really. So yes, so if here we assume perfect synchronization, because if we, I don't know if I have an empty, here, if you have like segments and then you try to distribute these segments, you're gonna have scenarios like this where one segment would be connected to 3 devices in the next layer, right? So you have to assume that there is perfect synchronization here to perform the inference operation, okay, that the output of this segment would reach all the 3 segments, all the 3 devices, sorry, okay, pretty much at the same time, so you can perform the inference. So this synchronization is implicit in this model. It would be, I thought about this, it would be really interesting to analyze the asynchrony as part of this problem, which we did not address. We did not address. What is the effect of asynchronous communication where the outcome from some segments, they arrive at different times at different IoT devices? What is the effect of this on the inference operation end to end? I really, we did not analyze that.
Yes, this is a really rich problem, like really it's interesting. What I really like about this work is that it's different from what I see in the literature. It takes, like everything that we see in the literature, takes the branch of learning The branch of like inference, I don't see much work. So this is really interesting in this sense, to be honest.
Yes,
great
what
stuff.
I highlighted. That's what I highlighted at the beginning. I really for those of you who are interested to tackle some some interesting areas. The area of distributed inference is not really that widely explored. Especially distributed inference, where you have a pre-trained model and you try to distribute the inference operation across the different IoT devices. That's not in the literature, and we plan to have a paper about this particular work. Really, I don't know. Do you want to move to the next one? It's up to you, Dr. Ayman.
So maybe we will take a break for Maghrib for maybe 5-10 minutes, and then we continue with whoever wants to continue. I think our students are here, so we can continue with them. But what do you feel? Because I feel it's Maghrib time, so maybe we need to take like maximum 10 minutes and then continue with the students. But if your second part will finish quickly, maybe we can finish it and then take a break. Up to you.
Doctor, we have finished 1/4. I only covered 1 minute. Okay.
Okay, then, because I know the
so
second
we have 3 more.
No, inshallah, we'll continue with the students. So with the students and anybody who wants to continue. So we'll take maybe 10 minutes break. We will go pray. We'll come back at 5:10.
Okay.
Let's try to come back at 5:10.
I can cover the layer-based model, because this one is pretty quick, and then maybe leave the distributed learning to another time. It's up to you, yani. But we can decide after we come back, inshallah. So we'll have 10 minutes break, inshallah.
Yes, inshallah. Thank you. So we'll be here. We'll be back in 10 minutes, and then we will continue with the distributed inference and maybe distributed learning. Thank you.
We'll see. Okay.
So our student, Shehel, Noura, Marwan, and actually a lot of our audience is with us too. So we'll start now, inshallah. Go ahead.
I hope we did not pour people with lots of information and they got bored.
No, it was very good actually. For that paper, it was very good, but it took its time. It's like a whole piece of work.
Yes. Yeah. I covered actually 2 papers, not one. Yeah.
Yes, 2 papers. Yeah.
Yes. And I tried to train myself in the meantime. عشان بس writing too much lines on the slide, and I was not able to clear them. So I knew how to do that. So I'm learning new tricks. Anyway, so as another as another sub branch for distributed inference, where we talk about layer based. So we have motivated the segment-based distribution for the machine learning model for the particular case, for addressing particular issues related to security. And we have shown that through the black box analysis that we have done. If security is not an issue for the IoT network, in that case, layer-based is actually possible. And in fact, it's even more desirable, because if you have one layer in one IoT device, another layer in another IoT device. So you have one-to-one communication link. So you don't have this one-to-many communication links that you need to address synchronization and all of this. So that doesn't have to be addressed for the layer base. So the layer base is a cleaner way of distributing the machine learning model. However, it's not possible in all cases, particularly for security issues. So this layer base tries to address another aspect or dimension for network dynamics, which in that case, mobility in a multi-drone system. So again, multi-drone systems are very commonly known to perform intensive surveillance and inference operations. And in that case, the drones, they fly and they are mobile in nature. So for that particular case, we need to divide the machine learning model, in that case, layer-based distribution, where we divide the different layers across the different drones in that case, while we try to address again the resource limitations on each drone in terms of memory and computation, but more importantly, trying to address the mobility aspects of these drones. Because if you assume that you have one layer here and one layer here, and these two drones, after like 2 or 3 seconds, they become out of range of each other, the inference operation will not be feasible in that case. Okay, so we have to strategically position the layers in such a way that takes into consideration the mobility patterns of these drones. So to do that, we have done some mobility analysis in that case, where we studied the different mobility patterns for the drone swarm formations. And we classified the mobility aspects of the drone into swarm formations. Homogeneous swarm formations are like 1, 2, and 4, where they are in fact fixed in relation to each other. Okay, so in other words, the distances between any two drones does not change over time a lot. That will in fact help us to try to position the layers on the drones without having to worry so much on the mobility patterns of these drones, because for homogeneous swarm formations, the drones, they don't change their positions in relation to each other a lot. Other mobility patterns, like they actually move in groups in such a way that they change their relative position with respect to each other a lot. However, because we are talking about swarm formation, they actually move in groups. They move in a group or two groups or something like that. So this type of challenging for the layer distribution, and they require special handling in terms of trying to predict the relative positions of the drones in the future in order to allocate or to distribute the layers. All right. So with that said, we try to again model this problem, but this time the objective itself changes significantly, because as you can see here, there's no, as you can see, there is no maximum, because again, it's not segment based, it's actually layer based. So we try to minimize the latency in terms of the time required to move the outcome of one layer to the next device. And we try to do that layer by layer, and we try to find the best combinations of the drones on which we need to allocate these layers to address a group of incoming requests, R, where R is from 1 to capital R, which are the total number of requests coming into the system. And if we need to address some mobility issues, we need to do that in predictable or in future time steps in such a way that minimizes this latency regardless of the relative positions between the drones in the future. Okay, and again, this is sorry. So, and again, the remaining part of the optimization problem is the same. So we have memory constraints, computational constraints, and so on. Here we do not have security constraints, of course. So security is not an issue in this particular case. So therefore, the layer-based distribution is possible. We try to estimate the rate between each two drones based on a simple path loss model, which takes into consideration the destination between the two drones, and the rate would be estimated based on that. So, so very quickly, we see that for homogeneous swarm formations, we don't really have to worry so much about the future time, because the relative positions of the drones, as we have seen, is not significant, and it does not change frequently over time. Okay, so here we have compared the optimal. So this is the optimal. The green one is the optimal, the solution to the optimal problem, to the optimization problem, and we have compared that with 3 other heuristics where we distribute the layer to the nearest drone in a greedy manner. Okay, so the next layer always goes to the nearest drone, to me. Okay. Or the highest residual memory, or the drone with the highest remaining amount of memory, okay, or with a combination between the nearest and the highest residual memory in a trade-off manner, okay. And as we can see, طبعا يعني for solving the optimization, it gives the best performance in terms of minimizing the latency, and there is a significant performance difference between the optimal solution and the nearest heuristic. Of course, this becomes even more challenging when the drones are mobile in a stochastic way, like using this reference group model, number 3. Okay, so in that case, the relative positions of the drones, it changes a lot, and in that case, having a mobility prediction has to be part of the optimization problem in order to distribute the layers on strategic nodes that will not change the relative position to each other in the future. Okay, so in that
I have a question.
Yeah, sorry, go ahead.
Yes, can you go back for one slide? It's slide 25. Yes,
this one.
You are minimizing according to the number of requests. So
yes,
the number of requests here is distributed in the system according to what is the scenario that you are following in the number of requests.
You have a set of incoming requests.
Yes.
The incoming request is defined by a request to perform an inference operation from the source node, okay, all the way to the end system, which in that case it could be like the command and control system on the ground, مثلا. So you are really trying to perceive a scene by the drones, okay, and you are trying to interpret what that scene is all about. Like, for example, a set of intruding people to the borders, مثلا. Okay, so you are trying to detect using computer vision. Okay, so the machine learning model itself is not of big concern to us, except that we need to distribute this machine learning model across the drones. Okay, but the request is a request for detecting a specific scene context, okay, using this machine learning model. Okay, I'm not sure if that's if that's clear. So you have incoming requests to the system. Each request represents a request to perform inference to a specific scene context. Is that clear ولا لسه مش مفهوم؟
Yes, thank you so much.
Okay, but the new aspect here, which has not been addressed at all in the previous work, is the time aspect. And the time aspect here is addressed because of the mobility nature of the drones. So we want to make sure that when we distribute these layers across the drones, that these drones will stay connected in the near future, at least for the next 10 to 20 seconds or 30 seconds, they will still be in range to each other. Okay, if the swarm formation is homogeneous, we don't have to worry about that, because again, the relative position between the drones, it does not change much, although the whole swarm formation, it moves in a specific direction. However, they don't change the relative position to each other. Okay, so we have compared the same optimization solution with mobility prediction in that case. And the mobility prediction in that case is performed based on knowing the distribution of the drone mobility. So we know beforehand that the drones will move in using the reference group model mobility. Okay, reference group model mobility is a well-established mobility pattern which allows you to estimate the relative location of the drones in the near future. And we try to do that for 10 future time steps. Okay, so at this point of time, we have performed mobility prediction. We knew the locations of the drones with respect to each other in the following 10 time steps. And based on that, we have distributed the layers across the different drones. So that's why you see that the latency is almost fixed for the entire 10 time steps, because we know in the future that these drones will still be in communication with each other. Unlike another state-of-the-art technique, which is in the literature, that does not take into consideration the mobility prediction. So we see that the latency starts to increase, and at some point, the drones, they become out of range from each other. And in that case, the communication is totally disconnected, and the inference operation is totally halted in that case. Okay. So that's again the distributed inference, and at this time we address the mobility aspect of the drones. So,
Dr. Amr, excuse me, I have a question. What about the performance with respect to the number of layers?
That's a good question. This is done using homogeneous requests, where we know beforehand that the request is a machine learning model using, like, for example, LeNet or VGG16 or something like this. Okay, so regardless of the number of layers, as long as we have enough drones with enough computational and memory capability to handle the layers in the machine learning model, we that's what this distribution algorithm is all about.
But
okay?
the latency.
So the number of layers will affect, again, the number of drones needed to accommodate these layers.
Also,
okay?
the latency.
So if the number,
also the latency will be affected by the number of layers.
Yes, you are right. You are right. In the paper, by the way, there is some result to estimate the latency as a function of the number of drones. You are perfectly right. So and you are perfectly right that as we have more and more drones, the latency should be reduced. Particularly, the number of rejected requests will be reduced. Okay.
Yes.
More importantly, the number of accommodated requests should be more as the number of drones grow more, right? Yeah. And if you have less number of drones, then the degrees of freedom that you have is less, and in which case, at some point, you might have to reject many requests. Many incoming requests you have to reject because you do not have enough drones to handle this. Okay.
Yes, so we can have adaptive structure for the number of, or compared to the number of drones available.
Yes. So if you want to change the optimization problem, instead of minimizing the latency, you could actually minimize the number of drones engaged in the inference operation.
Yes.
That's a different objective in that case.
Okay.
So currently the objective is to try to minimize the end-to-end latency for the inference operation, and the layers are allocated such that we meet the computation and memory constraints on each drone. But if you want to minimize the number of drones engaged, that's a totally different objective. Okay.
Thank you.
So the mobility part was maybe a little bit less comprehensive because we are still working on that. By the way, another approach to address the mobility, because it's another stochastic dimension for the network dynamics. So another approach, as you can imagine, to solve the same optimization problem is using reinforcement learning. So that's what we are trying to do now, and really designing the reinforcement learning agent to learn the mobility pattern of the drones automatically is a very interesting piece of work that we are currently trying to work on. Okay. So, Dr. Ayman, what do you suggest? Should we move on, or should we stop at this point? It's up to you.
No, continue. I think you are picking up the speed.
Yes, continue, right. Doctor. It's interesting.
Okay, so on the distributed learning part here, the machine learning model is not even trained. Okay, and we are trying to learn in real time in a distributed way. And here, as I said before, this branch is quite intensively addressed in the literature in two sub areas, including federated learning, where the machine learning model has some weights that change over time, and we are trying to calculate the weights in a distributed way, as we will see. And the other branch here is multi-agent reinforcement learning. So unlike the single agent, we can deploy agents in distributed manner to perform some distributed optimization, as we will see next. Okay. Type. So what is the motivation? What is the motivation behind distributed learning? So why not send all the data, from the IoT devices or from the devices themselves, send these data to the cloud, and in the cloud perform the training, okay, and that's it. So why not do that? Why we shouldn't do that? We shouldn't do that because in many applications, individual users cannot share their private data. They cannot. Okay. So their data cannot be shared with the cloud. So they cannot send the data to the cloud exposed, because this will have some privacy issues. Also, due to some scalability, as we have seen before, and I have explained this in the motivation part, that this will have an effect on the scalability by having massive data streams between the IoT devices and the cloud. And in that case, scalability would be an issue. Instead, what they try to do is that they don't actually send data, they send model hyperparameters. They send the machine learning model hyperparameters as opposed to the actual data. So in that case, there is no privacy issue. And the distributed learning here tries to enhance and maximize the accuracy through some collective wisdom. So here we are trying to learn from massive number of users. Like, for example, I can tell you an application. Like we are trying to detect a pandemic like COVID-19. So we are trying to do this through data from the different users, right? So one way is to get the data from all the users and then perform all the prediction at the cloud, which will have some privacy issues. Although in some cases privacy issues might be breached, but in other words, the privacy is in some cases very important. And we are trying to learn or predict this pandemic through massive data coming from hundreds or thousands of users in the country. Okay, so in that case, instead of sharing the data, we have actual prediction model deployed on the user level. Okay, and instead of exchanging data, we exchange model hyperparameters. So more specifically, so for federated learning, for example, the idea is as follows. So the individual devices will receive data or will use specific data which are different in nature. So of course, the data experienced by individual users are inherently and statistically different. Okay, and then this data can be used at every single device, and we can perform some weight updates. So for machine learning, we know that we have weights and biases, and these are the parameters that can be iteratively estimated at each device level. And after certain amount of iterations or episodes, we actually send the weights themselves, okay, to the cloud. So this is not the actual data. In that case, it's the weights, okay? And at the cloud level, what we do is that we use a very well-established theory, which is called federated average. So we perform basically estimation for weights at the cloud level, which is the average of the weights provided by each user, okay? And then after estimating this federated average, we send the weights back to the individual users, and supposedly by doing this iteratively and in a cyclic manner, over time, we do the learning in a more efficient way, and the model accuracy will be enhanced through gathering or collectively understanding the statistical aspects of the data from hundreds of users. So what we call the collective wisdom. So learning through collective wisdom, okay? And then we do that in a cyclic manner, iteratively like this. So over time, we should converge in such a way that we maximize the accuracy of the entire machine learning model. Okay, so the learning process in that case is done iteratively and in real time. So the state of the art when it comes to federated learning is what we call hierarchical federated learning. So for hierarchical federated learning, we have edge nodes which are close to the devices. Okay, and then we perform the same learning operation in a hierarchical manner. So first, we perform an iterative estimation of the weights at the device level. We send this weight to the edge first, and then the edge would perform a federated average step, okay? And then these edges will then send the average weights to the cloud, which again, it performs another level of federated average, okay? So in that case, we perform hierarchical federated average steps, okay? So this, we'll see the benefit of this hierarchical federated learning architecture in a minute. So the objective in that case is to try to optimize the model sharing of weights, okay, between the IoT devices and the edge, okay, to try to, on one hand, speed up the conversions, and on another hand, maximize the accuracy. Okay, so we try to speed up the conversions and maximize the accuracy at the same time. Okay, through the concept of, as I said, collective wisdom. And the challenge here is that the data at the different user level is statistically different. So for example, if I want to detect a certain health-related disorder, okay, I'm trying to deploy a machine learning model that remotely detects a certain health disorder, like for example, heart attack or a seizure, a patient who's having seizure or something like this. Okay, so in that case, I would not expect a single user to have data enough to detect all the different classes. Okay, the classes here being, for example, the severity of the heart attack, or the severity of the seizure, or the location of the seizure, and so on. So in general, you have multiple classes, like let's say like 10 different classes, and I'm not expecting each individual user to have all the 10 classes. Of course, naturally, we have a certain type of disorder. Each user will have one or two maximum types of disorder. Another application where, again, like for example, Ooredoo, they are trying to detect the type of traffic, okay, from different users in order to enhance their broadband service. So again, I'm not expecting a single user to do all the different services at all times. So I'm expecting, for example, certain types of users, they do gaming more than watching TV. Other users, they do watch TV more than browsing the internet or something like this. Okay, so in that case, the different data that exists at different users is statistically different. So we call it non-IID. We call this type of data set non-IID, which stands for non-identical and statistically different data. Okay. And again, we have to take into consideration the topology constraints of the network. So for example, not every node would have access to all the edges. So I need to take into consideration some network topology constraints. All right. So in order to perform this federated learning in a distributed manner, we know that the centralized model simply tries to minimize a loss function. And this loss function is based on the cross entropy. So the people from machine learning, they would know this loss function, the cross entropy. And we are trying to estimate the weights based on negative, the gradient, okay? And of course, they use the stochastic gradient descent in that case to avoid, having to estimate the gradient based on the whole data set. So these weights are estimated iteratively, but this model assumes that all the data set exists in the cloud, which is not possible in our case because the data is distributed at the different users, right? So instead, what we need to do is that at the user device level, we need to estimate, okay, the local weights, which is based on a specific edge and a specific user, okay, based on the local gradient descent, based on part of the data set that exists at this user, okay? And then these weights can be averaged using the federated average at two steps. The first step, after T- iterations, we perform the federated average at the edge level, at each edge, okay? And then from the M edges, okay, we perform another federated average stage at the cloud level. So after T- steps, we do at the edge, and after T- other steps, we do the federated average at the cloud. Okay, so the idea here is that This is the distributed weights. Okay, so these are the distributed weights of the model given the federated learning paradigm that we just explained. This is the centralized weights. Okay, so the idea now is to minimize, is to try to minimize the magnitude, okay, of the difference between the federated weights and the centralized weights. And this is what we call the divergence factor. Okay. So the divergence factor is in fact the difference or the magnitude difference between the centralized weights and the federated weights. All right. So in the paper, we actually go, I mean, the researcher goes intensively in the calculation to try to prove that this divergence factor is indeed proportional to the proportion of the data at each edge node and the distribution of the data at each node, okay, which is a multiplication of those two components. The proportion of the data, so how much of the data set exists at each edge node, and what is the distribution of this data. And again, someone might ask, if you know the distribution, you know the data, and the answer is no. Just the fact that you know the distribution of the data, it doesn't mean that you know the actual data itself, okay? So by distribution here, I mean how much time this edge sees that the person is having seizure, for example, or having a heart attack. But I didn't know exactly who is the person who is having seizure and at what time and so on and so forth. So knowing the distribution is actually a prerequisite to perform this minimization for the divergence factor. So in this work, the parameter that we have taken in order to minimize this divergence factor was how to assign the individual devices to particular edges. Okay, so this X here is the decision variable, which really represents which device should be attached to which edge node in such a way that minimizes this divergence factor. Okay, so this optimization problem is a nonlinear integer program in nature because both the R and the D are actually function of X, okay, which makes this problem nonlinear integer program in nature. And of course, we have another constraint here, which is the topology constraint. So which node can reach, so how many, so for example, one node has access to how many edges? So if all nodes have access to all edges, then you have very high degree of freedom, and you can assign the node to the edge that gives you the minimum divergence factor in that case. Okay. So that's the problem, and the results here show that indeed the optimization. So the green curve here is for the centralized weights, where the data set exists totally in the cloud, and we perform the weight estimation at the cloud level only. Okay, whereas the yellow curves here, they represent the estimated accuracy and the convergence of the loss function, okay, by assigning the devices to the edges in a strategic way, in such a way that tries to again minimize this divergence factor. And as we performed that, of course, on different data sets, the MNest and the SciFar data sets, and we can see significant performance enhancement, okay, based on normal federated learning. So this red this curve here is the non-hierarchical case, where the weights are learned based on the current distribution of data at the device without having to have edges that participate in the hierarchical federated learning. So in that case, the performance enhancement using the hierarchical federated learning is not only significant in terms of enhancing the security, enhancing the accuracy, but also significant in terms of speed. So we can reach to the same accuracy level much faster. Okay, so here we have to have like almost 100 rounds of exchange of weights between the edge and the clouds, okay, in order to reach to an accuracy level of close to 84%, okay, which in that case is reached using the optimal allocation at only like 10 different or 12 different communication routes. So in that case, this table here shows the performance enhancement in terms of accuracy and speed, okay, as we increase row. And row here, it means the number of edges that each node has access to. So as we increase row, this means that we don't have any topology constraints, which means that each node has access to as many edges as it wants. And in that case, we assign the node to the edges strategically in order to improve or to optimize the speed and the accuracy levels. Okay, so this is the federated learning part, and here we have tried to conduct a hierarchical federated learning, okay, by understanding the statistical differences between the local data sets that exist at different users, and then by assigning these users to strategic edges, we were able to enhance the convergence performance significantly using the hierarchical federated learning. So before we move to the next part, let's just take some questions for this part.
Okay, can I start?
Go ahead.
تفضل.
Okay, thank you, Professor Amr, for this valuable explanation. I have just a question for, please, can you go to problem formulation?
The optimization problem, this one?
No, the previous slide.
Yes, this one?
Yes, for the cross entropy, I think the formula has a negative sign at the beginning.
The what? Which one?
For the formula of cross entropy.
Oh, negative sign here?
Yes.
This is the loss function.
Yes.
Okay.
There's a minus.
So if there is a minus here before this?
Yes.
Could be. I have to double check, but I think the cross entropy, it could be. I don't know. But okay. So we can double check that.
Okay. The second question: how to group the users, or how to assign the users to the edges? Should the users explicit or disclose their classes?
Oh yes, that's a good question. So here, this is the actual system model, right? Yes. So the idea here is that each device has part of the data set. Okay.
Okay.
So this data set, okay, at device I, we need to know the distribution of this data set. Okay. We need to know the distribution, not the actual data set. Remember, we need to know the distribution, which means that how much time this user, for example, sees a seizure or sees a heart attack or something like this, or how much, what is the percentage of time that this camera sees a cat, something like that. Okay, so based on the distribution of the local data set, what this optimal algorithm tries to do is to say, okay, so distribution, I need to assign this device this edge. Okay, for example,
I understood.
Or I need.
Okay.
Yeah. So this means that this level, this edge would have a data set that statistically closer to each other. Okay? And by doing this at this level as well, I try to make the data statistically closer to each other, which will affect the number of communication rounds, okay, that you have to go through in order to have conversions. So by assigning the node based on the statistical properties of the local data set to a specific edge, you try to minimize the communication rounds that you have to go through to achieve conversions. Okay?
Okay.
So that's what this work tries to do.
Okay, but Dr. Here, do you think the privacy will be violated?
The privacy would be violated if you need to know at the edge, if you need to know the data set at the device.
No, but
if you
here
need to know the data set at the device, then there is a privacy issue. But if you need to know the distribution of that data, then someone might argue that even this would be a privacy issue. But in that work to facilitate the distributed optimization, we need to have this assumption that the distribution of the local data set is known a priori. And by the way, this assumption is the basic assumption of maybe 50% of the work in this area. So not just this work. Okay, so we have to have this assumption in order to facilitate the mathematical analysis, because this paper, by the way, goes through very, very rigorous mathematical analysis to derive the boundaries of this divergence factor. Okay, so this divergence factor, which I have mentioned here. Okay, so in order to reach to that particular state, you have to do some rigorous mathematical analysis to know that the divergence factor is indeed proportional to the distribution of the data at the edge, and how to do this distribution and how to control it. To control it, of course, is to position or to attach a specific node to a specific edge. Okay, in order to minimize that divergence factor. Okay. And not only that, really, this work also goes through some rigorous systematic analysis to try to simplify this optimization problem, because this problem, although it looks simpler compared to the optimization problems we talked about before, however, this problem is highly complex because it's nonlinear integer program. And in the paper, we actually try to simplify this through multiple steps to try to use some of the common techniques like branch and bound techniques to make the solution of this problem more efficient. Okay.
Okay, I have one last question, please, regarding the system model. The system model. Please, can you go to the system model?
Yeah, تفضل.
Okay, now for federated stochastic gradient descent, the edge user should repeat or should send the update every single local step, right?
صح.
While for
it's clear that you are deeply into that area. Yes, you're right. You're right.
خبير ما شاء الله عليه. This is his core area.
Okay, go ahead.
Okay, do you think this will be extensive regarding the communication resources?
Of course not, but the assumption here is that the communication between the edge and the device is very low cost. That's why really we have this edge, because the edges are supposed to be close to the devices in such a way that allows you to use very low power communication, like for example Bluetooth or LoRa or something like this.
Okay,
which will minimize.
Okay, but we have a model size. Sometimes the model size constitutes millions to billions of parameters, like CNN or dense nodes. Yeah, this will.
Yes, this will make the communication here quite expensive, and you are perfectly right. Remember here, the assumption of the fact that the weights are exchanged per iteration is to facilitate the statistical analysis. But empirically, you can use, you can exchange the weights every specific number of iterations. And this is what I have actually explained in this model here, right? So when I said that every T dash, okay, every T dash, you need to exchange the weights, right? So you can really exchange the weights every, like, for example, 100 iterations, which will make the communication cost even less. However, we had to make the assumption that this T dash equal to 1 only to facilitate the statistical or the mathematical derivations. Okay, so to facilitate the mathematical derivation and reach to that theorem, for example, we had to make the assumption that T dash is 1.
Okay, this is in case of using stochastic gradient descent.
Right.
If we have many batches, stochastic gradient descent, the imbalance data set will affect strongly the number of local updates.
Yes, you're right. Yes. Yes, صحيح. يعني ممكن, يعني I can really estimate the optimal T dash that minimizes the divergence factor. You are perfectly right, and this is actually the extension that we are trying to do now.
Okay.
However, for that particular work, we did not address this, and in order to minimize the divergence factor, we have simply assumed that T dash is 1 to facilitate the mathematical analysis, just to make it simpler. Okay. But again, analytically, you can use any arbitrary T dash. You are allowed to use any arbitrary T dash. There's no problem. Okay.
But we will have a problem with the synchronization.
Yes, طبعا. صح.
Yes.
هو actually, yeah, you are bringing a very interesting point here, is that here I did not even say that T dash is different from one device to another. In fact, you could have a different T dash from one device to another, in which case you have asynchronous communication, similar. So this is what you are referring to. So for example, if I have a device here and I have multiple edges or multiple devices, okay, and I'm trying to exchange the weights, okay, with these devices. So if T dash here is different from here, okay, then we end up with asynchronous communication. So what is the effect of this on the conversions? What is the effect of this on the accuracy?
It depends.
That requires some analysis.
Yeah, it depends on the distribution of the data itself.
صحيح, مظبوط. It depends. صح. It depends on the statistical distribution of the data, and also it depends on the communication cost between the devices. So some devices they would have, for example, better wireless channel gain, in which case exchanging the weights more often would not be that expensive. Other devices, they will have low channel gain, in which case the communication would be very, very expensive. So you would want to exchange the weights less often.
Okay, but
so we have thought about all these issues, but in terms of mathematical analysis, we had to make certain assumptions to rule out some of these aspects and focus on particular aspects that are addressed in this particular work. تفضل.
Okay, for the channel gain between the edge server and the end users, I think there is a selection phase in this in federated learning.
Yes.
To the learning. So this problem can be considered at the edge level.
يعني احنا we do it at the edge level, yes. Here now we do it at the edge level, but what I'm trying to say is that if you have let me see, if you have مثلا multiple devices here and you have an edge node, okay, so the channel gain between these devices and the edge node is different, okay. So for example, if this device sends to the edge more often, it's okay because the channel gain is really high and the communication cost would not be that high. Yes. Because of the fact that this link is really good. This device is a poor device and the link between it and the edge is not as good as other devices. So in that case, you need to exchange the weights less often. But in all cases, they all exchange the weights with the edge. But if they change, if they exchange these weights using different frequencies, or in other words, different T-dash, what is the effect of this on the accuracy, on the speed of conversions, on this kind of things? That's what needs more analysis. And we did not address that as part of this work.
Also, I think that the edge server can allocate more bandwidth to the users having.
That's exactly what we're doing now. That's exactly what we're trying to do now. But again, I mean, in order to try to optimize this, you have to have formulate an objective for the minimization function, and in that case, different because of the difference in the system model that you are proposing now. In this particular work, because of the assumptions we made, we were able to formulate the optimization problem using these particular components, which can be minimized in real time. Okay. But if you assume, for example, asynchronous communication, if you assume different channel gain, if you assume bandwidth provisioning, this will make the objective totally different, and the optimization problem will change drastically. And in fact, we are trying to do that now as part of the extension of this work. I think someone else is raising his hand. Hussam, تفضل.
Hello, Professor. No. It was just a mistake. Sorry for that.
Okay.
Dr. Amr, I have a question here too.
There is a question also. Go ahead, Malik.
Yes, sir. Actually, regarding the scalability of the solution here, the hierarchical one, we have scalability in the number of edges and the number of nodes. How to consider this one in your model?
The scalability is addressed in this model in multiple stages. First, really, the hierarchical nature of this model, okay, addresses the scalability, as we have, of course, talked in the very beginning of this presentation when we talked about the edge computing as a way to address scalability. So by exchanging the weights with the edges, that really should enhance the scalability issues. And this is what we have indeed seen from the results. If you take a look at the results here, so we have seen here from the results that this is the federated learning, the red. So this red curve is the federated learning without the edges. Okay, so this is the hierarchical federated learning part. So the performance has been enhanced a lot with the concept of hierarchical federated learning. But that's not the only stage where we address scalability. Also, another aspect of the solution, which I did not cover here, were to divide the users into groups. So for example, if you have hundreds of thousands of users in the country and you're trying to perform federated learning, of course, even with the edge computing, you're going to have a scalability issue, or you may have a scalability issue, in which case the first thing we do here is to try to logically group the users or cluster the users into groups such that each group of users, they would have the same statistical properties of the data set. So this group of users, they see a cat مثلا 50% of the time, and they see a dog 50% of the time, something like that. Okay, so by grouping, by this logical grouping of the users, okay, so we try to allocate group of users in one shot to the edge, okay, as opposed to single user. So this also addresses the scalability issue by allocating group of users to an edge, not a single user to an edge. So this makes actually the solution much faster and more scalable for large number of users.
Okay.
So these are different levels where we address the scalability. I'm very glad, by the way, with these questions, because it really enriches the discussion, and hopefully it's for the benefit of everyone. And I don't know. Now we can move to the last part of the multi-agent reinforcement learning. And I don't see any objection to move on, so I'll move on.
Go ahead. Go ahead.
Okay. All right. So, okay. So for this particular use case, what we have is, in fact, a smart health application over 5G networks. So this use case is particularly interesting because it addresses some of the issues that we have nowadays, like, for example, the COVID-19. And so the idea here is that for each individual user, we perform remote monitoring, okay? And here, what we're trying to do is that through the vital signs, each user will try to perform some processing using AI, okay, based on patient state, battery state, network state. So, for example, think about احتراز application, for example. So imagine hundreds of patients or hundreds of users across the country, they have احتراز application, right? And we need to make احتراز application more intelligent and smarter than what it really is now, okay? So first, we need to perform some customization of vital signs at each user level based on the patient state. For example, if the patient has seizure or the patient has heart attack, this vital sign becomes really, really important and critical, and it needs to be delivered to the cloud right away because there is some emergency case. And not only that, this vital sign needs to be very, very accurate, and there is no compromise to the accuracy of this vital sign because of the fact that patient is currently having a certain disorder. Okay, so based on that, the smart application at the patient level will perform what we call adaptive compression. So adaptive compression here is basically to try to compress these vital signs before delivery, okay? And then we try to split the compressed data across the different radio access networks. So 5G proposes heterogeneous architecture where you have heterogeneous types of networks. So for example, this one is 4G. This one, for example, is مثلا Wi-Fi. Okay, so each radio access network has certain resources that it can assign to the different user. Based on allocating the resources from the radio access technology to the individual users, users can deliver their vital signs with a specific performance. Okay. So again, the idea here is that based on the patient state, based on the battery level of the cell phone or the edge node, and based on the network state, how many RANs or how many radio access networks the user has access to, okay? In which case the user can split the traffic across the different RANs in order to get certain performance end-to-end. So the objective of this work is to try to find the optimal action policy at the patient level, which means what is the appropriate compression ratio level that we can use at the patient level. What is the split of the traffic across the different RANs in order to minimize the latency and maximize the battery lifetime over time, maximize the device lifetime in terms of battery, okay? But this is not the only objective. The other combined objective that goes with it is that at the network level, we need to also devise an optimal policy to allocate the resources in order to maximize the resources of the network, right? So you can think of it as a game where the users are trying to gain as much resources as possible from the different radio access networks, and at the same time, the radio access networks are trying to allocate the resources smartly to the different users in order to optimize their user experience, okay? And the challenge here is that the policy that you need to devise is in fact based on the patient state. And that's what's different about this work, is that we have to take the patient state into consideration. If the patient is having seizure, or the patient is having a heart attack, or any kind of disorder, I cannot assume that the data has to be transferred with the same level of urgency and with the same performance like the person who is normal. Okay, so I have to watch for the patient state. Not only that, I have to watch also for the battery level of the cell phone and so on. And also the solution scalability. So any centralized solution in that case would not be feasible because of the fact that I cannot assume that the network would tell the user, compress the data in this way. No, this decision has to be taken by the individual user. Okay, the network can allocate resources, but cannot allocate how the user is really customizing the data that is being transferred. All right, so these are the objective. This is يعني a very, very complex problem in that case. So in order to facilitate the optimization in this case, we devise different models. The first model is the adaptive compression model. And here the adaptive compression model tries to estimate the distortion of the data based on performing a certain compression to this data. And the distortion is the amount of information loss in this particular vital sign based on the fact that we compress the data up to that compression level. Okay, and here we have in fact done this adaptive compression using multiple techniques, using machine learning, using digital wavelet transform, using different techniques, and we can map these techniques to that mathematical model, which later on facilitates the optimization framework. The second model here is the energy model. The energy model is the amount of energy that I need to spend in order to send a unit of data to a particular radio access network. Okay, so this is based on the famous relay channel model. Okay, except that this model is in fact proportional to a specific parameters, which is psi j and cj, which are distinct for each radio access network. So each network would have different constants for psi j and cj. So by changing these constants, I make the each RAN more energy hungry or less energy hungry. Okay, so there are some energy requirements different for each RAN. The third model is the latency model, which is it's the simplest model, which is based on the estimated rate, okay, which is based on, again, the relay channel model. And based on that, we can estimate the latency model. So based on this, we have again solved this problem in two different ways. The first is using distributed optimization framework, where we have modeled the so we need to minimize a multi-objective problem in that case. So we have to minimize utility at the user level, by addressing the compromise or addressing the trade-off between three different components: the consumption at the device level, the monetary fund or the amount of money that you have to pay in order to send that data, and the latency or the amount of time that you have to spend to send unit of data to this particular radio access network. And also we need to minimize the distortion, in which case we need to preserve the quality of the vital signs. And we need to address the trade-off between all these four components. So we have four components in total. Okay, so the energy, the cost, the latency, and the distortion. Okay, so we need to find the optimal trade-off between all these four components. And this is, of course, subject to this is the bandwidth allocation from the network. And P here is the split factor, where we need to split the traffic from each user to different radio access network. And at each user, we also need to do a certain level of compression to the data. Okay, Kevin? So this optimization problem, as you can imagine, is really, really complex. Not only it's nonlinear, it's actually nonlinear in all these parameters. Okay, and in that case, it's really highly complex. And also, if we solve this problem in that way, the solution would be centralized, which, as I said before, it's not feasible for the network that we are talking about. So instead, what we did is that we have, in fact, divided this P1 problem into two sub-problems. Okay, so sub-problem one would run at the network and would try to do the bandwidth allocation at the network first. Okay, and once the network allocates the bandwidth, then we send the allocated bandwidth to the individual users, and the users would then try to run the second sub-problem, where they need to split the vital signs across the different radio access network, and they will need to estimate the compression level at each user. And they need to do that iteratively, as we will see in a minute. So we went further and we tried to subdivide sub-problem 2 into two sub-problems to try to simplify the solution even more. And we performed these two sub-problems in some cases using some closed form solution, which speeds up the overall solution significantly. So this is the overall algorithm, which we call it ONSRA, or Optimal Network Selection and Radio Resource Allocation. Okay, ONSRA. Okay, so the idea of this algorithm is that first we try to solve the sub-problem 1 at each individual radio access network to try to allocate the bandwidth. Okay, by solving a small optimization problem at each RAN, okay, localized. And then after we do this, we send the allocated bandwidth to the individual users, and individual users can then run the sub-problem 2 by trying to estimate the optimal network indicators, how they will split their traffic across the different RANs, and what is the compression level that they need to have locally at each user. Okay, and we do that iteratively until we achieve certain conversions. So basically, by doing this sub-problems, we have divided the big problem into smaller sub-problems that can be solved in a distributed manner. And by the way, this is not using AI. Yani, until now, we are not using AI. The AI will come next. Okay. So the results here show that this particular distributed optimization is indeed relatively efficient. And here we compared this optimization solution with two state-of-the-art solutions. One is by assuming a simple model at the network that the network allocates resources equally between users. And this heuristic assumes that the traffic is split equally on all RANs. Okay, so by making this comparison, we can see that blue curve here represents the UNSRA, or the proposed optimization algorithm, which outperforms significantly the other heuristics or the other state-of-the-art techniques by significant amounts. And also we notice here is that the iterations that are required to reach to the optimal solution are really quite low. So in some cases, we need to go between the RANs and the users maybe 2 times only to reach to the final solution, which is relatively good news, that this can really perform a good performance overall. Okay, right. So we were able to see how the different RANs now, we have 3 RANs. One of them is 4G, 5G, and Wi-Fi. And of course, each one of them would have different communication requirements and different resources, and of course, different rates, allocation, and so on. And we were able to see that the user 1, which is the pervasive edge node 1, the user edge 1 has the biggest or the largest size of data, and in that case, it allocates big part of this traffic to RAN 1, because RAN 1 can give the highest bandwidth, and RAN 2 because RAN 2 is 4G and it gives the highest bandwidth. So the majority of the traffic for this user is split between RAN 1 and RAN 2, and in that case, the other users can compete on the other shares or the other resources from these RANs. Okay, so we also can see the performance in terms of how each user. So we have here in total about 5 UEs, 5 user equipments, how the individual users can split their traffic across the different RANs. And again, user 1 with the highest or the largest amount of data, how it splits that across the different RANs. And here we see that for the last curve here, we see that the compression ratio is the highest for user 1, because user 1 has the highest or the largest amount of data. So we try to compress the data before delivery in a much higher way compared to the other users. Okay, so this work, by the way, did not take into consideration the patient state and did not take into consideration the evolution of the bandwidth allocation across a long period of time. In other words, this optimization problem or this solution is greedy in time, is greedy with respect to time. Okay. So the other approach here is to try to use a multi-agent reinforcement learning. So for multi-agent reinforcement learning, we have 2 tiers or 2 types of agents in that case. We have agents that are running at the user level, and we have agents that are running at the network level. Okay, so which means that this is not only multi-agent reinforcement learning, it's multi-heterogeneous reinforcement learning agents. Okay, so each type of agent, we call it's a team-based, which means that each type of agent is actually grouped in a team, that they need to cooperate together at a certain level in order to perform the optimization problem. So, for example, at the user level, the action would be, I need to split the traffic using this PIJ, and I need to perform certain compression level. At the RAN level, the action would be, what is the share of bandwidth for each user, okay, that is taken from this RAN. In terms of states, the states for the user agent would take into consideration the energy, the cost, the monetary cost, the latency, the distortion, and the patient state, and the residual battery level. So these parameters constitute the states at the patient level. At the network level, the state is simply how many of these users are allocated to this RAN so that we can perform the bandwidth allocation to this number of users. So based on that, we estimate, or we try to calculate the reward based here, very important, based on the patient state. So if the patient state is 1, this means that the patient, for example, has seizure. If the patient state is 1, here we see that we don't actually care about energy. We don't care about anything other than latency. So even if we have to spend more energy, we need to send this data very, very urgently to the cloud in the lowest latency possible, even if we have to spend very high amount of energy. Okay. And here the word is simply based on the allocated rates for each user based on the bandwidth allocation. What is the average rates from each user, which is proportional to the reward that this RAN would get. So this is the distributed architecture for the multi-agent. So here we are using a specific class of reinforcement learning called the deterministic DDPG. Okay, distributed deterministic policy gradient. I cannot emphasize enough that this type of problems is really, really complicated because all the parameters that we are trying to allocate here are continuous in nature. Specifically, the bandwidth, the compression level, and so on. These are all continuous in nature. So we cannot use the DQN directly, or the deep Q network. We have to use DDPG or the policy gradient in order to find the best set of actions that we can take at any point of time. And this architecture is quite complex, to be honest. So it assumes that you have, for each user, you have to run 2 machine learning models. One is called the actor and one is called the critique. If any of you is familiar with the DRL architectures, so we are using an actor critique model, which assumes two machine learning models running at each entity. So we have 2 machine learning models running at the user level and 2 machine learning models running at the access point or at the RAN level. These networks or these machine learning models, they are interacting with each other using some replay buffers, which represent the amount of cooperation that has to happen between these different agents. Okay, so by doing this is in fact the learning architecture. So the bad news is that this learning architecture is very, very complex, and someone might argue that the amount of complexity here overweighs the value of the multi-agent reinforcement learning solution, because you have to deploy all these machine learning models at the user level and at the network level. The slight good news here is that the execution or the exploitation or the actual deployed architecture is quite simple. So you have only 1 machine learning model at each user, okay? And this is after the learning phase. So after the learning phase, the exploitation phase can be conducted using only 1 machine learning model at each entity, okay? So very quickly, again, the first step for each reinforcement learning is again to analyze the conversions. And here, luckily, we were able to achieve conversions at all the entities. So all the different RANs, they converge, okay, in a distributed manner. So even the learning of the actions and the observations can happen in real time, and we can achieve the distributed conversions. And also, we can achieve conversions at the user level, at the user agent level. Okay, so these are, very good news that conversions is attained in, or it's achievable in multi-agent distributed way. And the last but not least, we can see the results in terms of the overall average reward. Here, interestingly speaking, here we see a drop in the reward, and the reason here is that here we have an event, we have a seizure event here for the patient. Okay, so a patient at this point of time, probabilistically كده, it happened that this seizure is this patient is having a disorder or is having a seizure, in which case we need to deliver the vital signs to the cloud in a very urgent manner, and in that case we need to sacrifice the energy and we need to sacrifice everything for the sake of latency. Okay, and the good news here is that we can see that using the multi-agent DDPG, okay, it outperforms the optimization solution that we have covered before by a significant amount. So the battery level, this battery level can last at least 50% longer compared to the optimization solution, just by using the multi-agent reinforcement learning. Okay, even you see the pump here again. This is based on the seizure event that happened to the patient, and in that case, the energy level or the battery level drops a little bit drastically because of the event, the disorder that happened to the patient. We see, of course, the peak of the energy consumption that happened here again due to the patient state. So the patient state here is taken into consideration while you are doing the action at the user level and at the network level. And of course, how the event affected all the four components of the optimization problem in terms of the energy, the average latency, the average the cumulative memory, and the distortion level. I'm surprised that you have survived the presentation until now. So
yes, we did.
I'm really surprised, and I'm glad that you survived the presentation until now. So at the conclusion, pervasive edge computing can potentially enhance the scalability and the security of the IoT-based applications, as we have seen. Segment-based distributed inference is more efficient for security, and we have seen the black box attack analysis. The mobility prediction is essential for distributed inference, particularly for non-homogeneous drone swarm formation. And also the hierarchical federated learning can in fact have key performance enhancement to address the statistical differences of the data properties. And finally, the multi-agent reinforcement learning is promising for scalability and for solving very, very complex optimization problem in a distributed way, as we have seen. So finally, I cannot really ignore the efforts of the group members. We have really a plethora of bright minds of researchers particularly, and I would like to commend them for their excellent work. Of course, we have more members in our group, but these are the group members that I just summarized their work, and of course the supervisors from HBQ and from Qatar University. Okay, so thank you very much.
Thank you so much, Dr. Amr, for this very nice seminar / tutorial in a very complex area and very hot and recent area. So I don't know if people have questions maybe about the last part, the multi-run.
I don't know if they are still awake.
No, they are. We have still.
Yes, actually, I have questions, please, regarding the last part.
Okay.
Yes,
yeah,
Malik.
Glad to answer.
This is his interest in area. Go ahead.
Regarding the role of the cloud here, what is the role of the cloud? We have seen the rats, we have seen the devices. What about the cloud?
The cloud performs the intelligence for the application. Here, what we are trying to do is to trying to optimize the policy for delivering the summarized information about these vital signs to the cloud. The cloud will perform further analysis. Like, for example, مثلا the person currently is having seizure. Okay, so for me, what I tried to solve now is that I tried to devise the optimal policy to deliver the piece of information that the person is having seizure in the very efficient way to the cloud. And then the cloud would say, okay, so I want, since the patient is having seizure, I want to analyze the vital signs even more to know, like, for example, what is the location of the seizure, what is the state of the patient while he's having seizure, and so on and so forth. But the cloud did not have a role in allocating the network resources or allocating the different actions at different user level. Not sure if this is clear enough.
So it is not an agent, right? How many agents you have? N users plus N rats? The cloud is not an agent, right?
Yeah, I have multiple rats in general. طبعا احنا for the sake of the results, we had only 3 RANs, and we had about 5 different patients. And the only reason for that is that the actual simulation of the amount of multi-agent distributed reinforcement learning, the simulation itself takes about 3-4 days. Because of the fact that all these agents are deployed in a virtualized environment, of course. So it's quite complex. If you distribute these agents across the different devices, of course, the scalability will be a lot better. So again, the objective here is to try to achieve the best policy in terms of taking actions at the user level and at the network level to try to optimize the delivery of the vital signs to the cloud.
Okay.
But then the assumption here is that the cloud has more analysis that it needs to do, which is outside of the scope of this. That's why there is no machine learning model in the cloud in that case. Fadl.
Yes, actually, I have a small comment, please, if you go to the results part.
Fadl.
The convergence of the models.
Yes. Sorry. The conversions of.
Yeah.
Yes.
Yes, actually, figure B, actually, if you see, I'd recommend that you extend the number of episodes here.
Yes, you're perfectly right. Yes. By the way, I had to say something. This is still a work in progress, by the way. Particularly this multi-agent. That's why I left it at the very, very last part of the presentation. There's still a work in progress, and we're still trying to optimize, actually, to try to redesign the learning architecture and the deployment architecture in a more efficient way. So it's still a work in progress, to be honest. But you are perfectly right. So we need to extend the learning part here in order to achieve more consistent conversions. You're right. You're perfectly right.
Yes, actually, my final question here. Go to the last results, please. The one just after this one. Here, the ONSRA and the PG. The ONSRA is the theoretical solution, you mean?
Yes, the theoretical optimization. Yes, but yeah, I have to say something here. As we said before, this theoretical optimization is actually greedy with respect to time, which means that it actually finds the optimal solution at an instance of time. It does not try to find an optimal policy over a long period of time. You see the difference?
Yeah. So can we consider
it tries to find the optimal action at this point of time without considering neither history nor future of how the parameters of the system would change. Like, for example, it doesn't take into consideration the battery level. So if the mobile device has a very low battery level, okay, the reinforcement learning can expect that, can predict that because of the fact that if I take this action, the battery level would drop significantly. I have to spend more time on data compression in order to optimize the battery level along at a long time horizon. The ONSRA, this one does not take into consideration the battery level in any way. Does not take that into consideration at all. Okay, so it tries to optimize the decision parameters at an instance of time without considering neither history nor future. That's the main difference. And that's why here you see that here at this point, we can see a significant enhancement in terms of the lifetime, almost by مثلا 30% or 40% and more. Like if we consider the performance difference with respect to the heuristic, it's almost 100%. So I can make the battery life for at least double the amount of time, okay, using the multi-agent reinforcement learning compared to the simple solution, the simple heuristic solution.
Yeah. So one last technical question regarding the denomination calculations. Consider the interference, or I guess we don't have an interference in this case since we have multiple rats, different rats, right?
Yes, you are perfectly right. We did not perform interference management in this particular problem. أنت شغال مع الدكتور محمد عبد الله صح؟
Yes.
Yeah, multi-rat reinforcement learning, multi-agent.
That's not the issue. The issue is that I know Dr. Muhammad Abdullah is physical layer guy, so I'm glad he's not here, or he would be more maybe more rigorous than his student in saying, okay, how come you did not address the interference management in this network? How come you go across the interference manager? I know there is no MIMO here, and so we did not consider physical layer issues. Who is asking? I need to know your name.
I am Malik.
Malik, you received a lot of questions from Malik and Abdul Latif, and these are actually their areas of work. So
that's very, very interesting questions. Mashallah, you are asking very good questions, Malik. Yes, really, we did not address interference management in this part, and we're considering that the communication that happens between the users and the rats has no effect on the interference to other users.
Okay. Thank you so much, Doctor. Thank you. Sorry for the question.
Thank you for
no, actually, excellent question. Really, we enjoy because this is really what are the value of this type of talk. So, any other questions from our students in the class? I know we almost reached the end of the class now. So, my promise to leave early maybe will not materialize today. So, Dr. Mohsen, you have any concluding questions?
It was a very nice and detailed presentation by Dr. Amr. Thank you, Dr. Amr, very much. I think you covered everything.
تنفع tutorial يا دكتور؟
It's a very good. It could be very good tutorial. Of course, with once we finalize the latest results, I think it will be very good tutorial indeed. Yeah. So it's good, mashallah. جزاك الله خير يا دكتور. شكرا على الدعوة يا دكتور أيمن. it was good.
يعطيك العافية. شكرا على حضورك وشكرا على حضوركم.
For those of you who don't know him, he's one of the key people.
It's not fair you put me the first one. You should be the first one.
No, I did not يعني mean to do it in any order. طبعا, you know, some familiar faces here for people from HBQ. So these faces might be familiar. Dr. Munir and Dr. Ayman, of course, and Dr. Abdullah is the head of our department. And in case you don't know me, I'm this guy.
Thank you very much. Thank you so much
No
for
problem.
the time and effort, and really beneficial for our students and for this course.